let's pursue the idea of circular orbits. Later in the course we will cover elliptical orbits, but now let's exclusively talk about circular orbits. Now this is the mass of the Earth, and in a circular orbit is an object with mass m, a satellite, and m is way, way, way smaller than the mass of the Earth, and the radius of the orbit is r, and this object has a certain velocity v, tangential speed. The speed doesn't change, but the direction changes, and there has to be a gravitational force to hold it in orbit, and the gravitational force is exactly the same as the centripetal force. We've discussed that many times before. And so the gravitational force, which is necessary to make it go around, I could also say the centripetal force is necessary to make it go around in a circle. That gravitational force equals m Earth g divided by r squared. This is now the distance from the Earth to the satellite, and that must be equal to m v squared divided by r. And that is that tangential speed that you see here, which a little later in time, of course, would be here. I lose my m, and so you see now that the orbital speed, not to be mistaken for escape velocity, the orbital speed is exactly the same what we have there, except the square root of 2 divided by r. This is now r, and there was r Earth. If you know r, then you can calculate the speed in orbit. If you know the speed in orbit, you can calculate r. And so the period of going around in the orbit t equals 2 pi r divided by the orbital speed. And when you do that, you get 2 pi, you get an r to the power 3/2, and you have downstairs the square root of g m Earth. Let me move this in a little. 2 pi r to the power 3/2. So again, if you know the radius, if you know how far you are away from the Earth, the period follows uniquely. If you know the period, then the distance to the satellite follows uniquely. If we take the shuttle as an example of a near-Earth orbit, so we have the shuttle. The shuttle may be 400 kilometers above the Earth's surface, so we have to add to the radius of the Earth 400 kilometers, so you end up with about 6,800 kilometers for the radius of the orbit of the shuttle, and you substitute that in here, the mass of the Earth and the gravitational constant, you'll find that t is about 90 minutes. It's about 1.5 hours. The shuttle takes about 1.5 hours to go around, and the speed, that tangential speed, is very close to 8 kilometers per second. And that holds for all near-Earth orbit satellites. Whether they are 400 or 500 or 600 kilometers, that doesn't change very much. If you take the moon is much further away than the shuttle, and you take the distance to the moon, which is some 385,000 kilometers, you substitute that in this equation, you will find that the period for the moon to go around the Earth is about 27.5 days. And its speed is only 1 kilometer per second. It's much further out. If it's much further out, r is much larger, and so you see the speed will be much lower. If you take the Earth itself around the Sun, because we can use all these equations, replace the mass of the Earth by the mass of the Sun, and then we can do this for planets. So if we take the Earth around the Sun, then we have to put in the mass of the Sun, which is about 2 times 10 to the 30 kilograms. And the distance from the Earth to the Sun, we have seen that before. I call that the distance from the Sun to the Earth, is about 150 million kilometers. Forgive me for mixing up meters with kilometers, but you have to convert that, of course, to meters. And when you calculate how long it takes the Earth to go around the Sun, no surprise, you'll find 365 5.5 days. So there's simply substitution of these two quantities in the equation that I have here and that I have here. The velocity of the Earth in orbit is about 30 kilometers per second. It's a substantial speed, by the way, that the Earth is going around the Sun, 30 kilometers per second, way higher than the speed that the shuttle is in around the orbit, around the Earth, which is only 8 kilometers per second. Jupiter is 5 times further away than the Earth, and so the time for Jupiter to go around goes with 5 to the power 1.5. That's about 12, so it takes Jupiter about 12 years to go around the Sun. Notice that this period is independent of the mass of the little satellite. And that was very unfortunate for the Americans when on October 4, 1957, Sputnik was launched. They could find the radius very easily because they knew the period that it took Sputnik to go around the Earth. That was about 96 minutes. They could calculate the velocity, they could calculate the radius, but they had no clue about the mass. And that was a key piece of ingredient that the Americans wanted, because if the mass was very large of Sputnik, that would indicate, of course, that the Russians had very powerful rockets. But you cannot tell the mass from the orbital parameters. It's independent of mass. Whether you have a very light object or a very heavy satellite, they have the same velocity in orbit if they are at the same distance and they have the same orbital period. I mentioned earlier, notice that the orbital period and the escape velocity vary by a square root of 2. If you are at a particular position, for instance, you're at a particular position around the Earth, here at a satellite, if you want to escape from this, you will need a speed which is the square root of 2 times larger than that orbital velocity. And so if you wanted to escape from the Earth, then you need your 11.2 kilometers. We have it there. If you are near Earth in orbit, you are 8 kilometers per second, and 8 times the square root of 2 is exactly that 11.2. So you see the connection is always through this square root of 2. There is something remarkable about these numbers. The total mechanical energy, and I will write that once more here, which is 1/2 mv squared at a given radius minus little m, capital M, g over r, whether m is the mass of the Sun or the Earth is of no concern to me now. This is the kinetic energy for something in orbit at this radius, and this is the potential energy. But now notice, I can substitute now for this v squared, I can substitute the square of this, that is the orbital speed, and then I get mg over r. And so this one equals 1/2 mg over r. And now compare the two. They almost look like carbon copies of each other. Except that there is a minus sign here, which is crucial, and there is a half here, which is missing here. And so the total energy E, which I've called the mechanical energy, always for a circular orbit, is 1/2 u and is the same as minus the kinetic energy. A remarkable coincidence, you would think. But it's not as much a coincidence as you think, of course. But if something is in orbit, this is the orbital speed at radius r, then always is its total energy is half the potential energy. It's always negative.